get the okay. There's a long latency because of all these acknowledgement and requests of retransmission. Okay, and it's actually connection oriented. Okay, meaning this IP connecting to that IP is pretty fast. Okay, now for multimedia, people come up with something called User Diagram Protocol, or UDP, which relax some of the constraints that we have over here. Okay, for example, we have no acknowledgement in UDP. Okay, basically UDP promised to offer us the best effort delivery. I'm going to try my best to get your package there, but there's no warranty. Okay, based on just statistical behavior. It has a much simpler protocol, and it doesn't have any connection-oriented. Okay. Now, RTP is another protocol that requires that we will use for real time. So it provides timestamp to resolve delay jitter. So it knows exactly. It provides not only the sequence number, but it also gives a timestamp on your packets. Okay, so that you know that what packets is right now waiting somewhere, and what is the type of delay. Okay. It provides payload type information. For example, it tells you what kind of video that you are transmitting. So this is part of the packet headers. Okay, and the payload format adds redundant information to the headers to eliminate data dependency between packets. So hopefully, this is an advanced protocol that tries to eliminate some of the problems with the redundant, with the dependency between your macro blocks, for example. It tries to eliminate that redundancy, so that if you lose something, the loss will be local and it will not spread out. Okay. So an example of the type of packets that being used for video streaming over the web will look like this. Okay, you have the source destination address, the regular IP address between the two computers. You have the UDP headers. Okay, you have the RTP headers, and then you have the payload, which is your real video stream. And then after that, you still have the trailer, the redundancy checkpoints. So it adds two more layers to the header information. Okay. So in the multimedia communications framework, we have a setup like this. Okay, so we already study this problem to death, right? We know what K is, what Q is, what E is, what E inverse is, what Q inverse is, what T inverse is. So this is our regular source coder, our regular source decoder. And before, what we did is we connect this phone to this phone and say, hey, my channel will be okay. Okay? That's not true. That's not true. In practice, your channel will not be okay. Your channel has a lot of problems. So we have to add this guy. We have to add this transport coder, and we have to add this transport decoder. Okay? In the transport coder, you have to do channel coding. So you have to do packetizations, and then you have to do the modulations that you need to transmit. Okay? So packetization means what?
Breaking the video to
exactly, into packets. Okay? Should you break it in a random way? No, you should not. Right? At least you have to go to the end of the marker block. Okay, at least it's easy to decode that way. Right? Imagine you have a packet that starts in the middle of a marker block. That is very difficult to decode, right? I mean, you don't know, then you have to, there's so much redundancy, there's so much dependency that you have to, for the next guy, you need the other one in order to decode this one. Okay, so you don't want to do something like that. You want, so source versus channel coding. We have been talking about source coding for 3 days now, right? So here, maybe I'll just say something real quick about channel coding. So who has experience with channel coding before? Okay, 1, 2, 3, 4. All right, so looks like I have to spend a little bit more time with channel coding. But let me do just a very simple example. There are many types of channel coding techniques. We heard about a few already, right? Low density parity check, okay, low density parity check, LDPC code. We heard about turbo codes, okay. I did mention Hamming somewhere, okay. So those are very popular type of channel coding techniques, okay. So the idea of channel coding is to protect error from happenings, okay. So to help with error detection, hopefully you can detect error and then maybe recover some of the errors and conceal some of the errors. Okay? So joint source and channel coding is still an active research area, and hopefully we're going to see that that the way channel coding works is actually very different from the way source coding works. Okay? In source coding, we take away redundancy. In channel coding, we add redundancy back in. Okay, it doesn't make any intuitive sense, but the type of redundancy that we add in for channel coding is very different from the type of redundancy that we take out from source coding. You add in very structured type of redundancy. Okay, you add your own redundancy, so you know exactly how it behaves. Okay, we take away redundancy from the source. Okay, but we don't really know exactly what type of redundancy it is. Okay, we only do transforms, we throw away the small guys, but that's about it. We don't really have very fine control. Okay, now so the word error resilience means any techniques that protect yourself from transmission error. Okay, error resilience means you are trying to come up with techniques to deal with error and make sure that you're robust with respect to error. Okay, so if you do multimedia over unreliable channels, for example, wireless, okay, it has a lot of problems. Okay, and even with internet, it has quite a bit of problems. Okay, not as much as wireless, of course, but still. Okay, so these are the type of unreliable channels that we have to worry about. The transmission errors in communications typically comes from two sources. Number one, random bit error. Random bit error means you either have a bit inversion, bit insertion, or bit deletion. Okay, you get a bit that wipe out completely, or you get an extra bit somewhere in your data, or you have a 0 is turned into 1 or 1 turns into a 0. Okay. So typically this is very common. It's not very common to have that because typically we have time windows, okay, that specify for bits. Okay. So bit inversion is very popular, and that's what we're trying to do in the next few slides, trying to protect ourselves from that problem. Now, we have bursty error. Bursty error is the packet loss that we just talked about. You can lose the entire packets because the router determines that, hey, I don't have enough buffer in my queue, so I cannot accept you. So that is the type of bursty error that we have to worry about. So error control goal and techniques is to overcome the effect of errors such that packet loss, such as packet loss, such as bit errors, so that you will be a lot more robust over a lossy communication. And these are the type of error control techniques that we will investigate. The easiest one of all, already being implemented in our internet protocol, is retransmission. Okay? So, if you check everything and discover that you have a problem, you call up the other guy and say, hey, send me that packet again. Okay? Well, you pay the price for the long delay jitter, but it's, if you're willing to wait, everything will be okay. Another part of error control is called forward error correction, which is the channel coding that you are familiar with. Error concealment is the techniques that allows error to happen, but rely on what you receive to correct the errors. So for example, you might lose a block somewhere in the middle of your video. Okay, how do you do concealment? Any idea?
Interpolation.
Yeah, you use interpolation. That's good. Interpolation in what?
One frame.
Temporal or spatial?
Both of them.
Yeah, can use both. Okay. In video, most likely temporal will work better because there's a lot more correlation in times. But if the block happens to be an intra-block, for example, then you have to use spatial interpolation, right? So it's very intuitive, but it works